Imagine, for a moment, that you are scrolling through your morning newsfeed. You stop at a headline that has become increasingly common in recent years. Astronomers discover new Earth-like planet in the habitable zone. Accompanying the text is a beautiful artist's impression, a marble of deep ocean blue, swirled with white clouds and vast continents of green, hanging peacefully in the velvet void. It looks like hope. It looks like a future home. Your mind inevitably drifts to the possibilities. You imagine vast alien forests, oceans teeming with exotic life, perhaps even a civilization looking back at us. It is a romantic, intoxicating thought. But here is the brutal reality that the headlines rarely tell you. That image is a lie. Not because the science is wrong, but because the universe plays a trick on us that is so cruel, so absolute, that our human brains struggle to comprehend it. The planet you are imagining, that lush blue paradise, is likely already dead. In fact, it might have been a burnt-out cinder for 1,000,000 years. We are not looking at a live broadcast of the universe. We are looking at a photo album of ghosts. To understand why most planets are dead before we ever discover them, we must first confront the most fundamental limitation of our existence, the speed of light. We are taught that light is fast, and on Earth, it is. It travels at 300,000 kilometers per second. In the B of an eye, it can circle our planet 7 times. But the moment you step outside our solar system, light stops being fast. It becomes agonizingly, painfully slow. The distances between the stars are so vast that they defy human intuition. We measure them in light years, the distance light travels in one single year, which is about 9.46 trillion kilometers. When we look at a star that is 1,000 light years away, we are not seeing it as it is today. We are seeing it as it was 1,000 years ago. We are looking into the deep past. This means that every telescope we build is effectively a time machine. But it is a time machine with a terrible flaw. It only looks backward. When we discover an exoplanet, a world orbiting another star, we are not discovering a place. We are discovering an echo. Consider Kepler 442b, a planet often cited as one of the most Earth-like worlds we have ever found. It sits approximately 1,200 light-years away. The light that hits our telescopes from that planet left its surface, whilst Europe was in the Dark Ages, long before the Industrial Revolution, before we split the atom, before we even knew what a planet was. If a cataclysmic event destroyed that world 500 years ago, an asteroid impact, a supervolcanic eruption, or a biological collapse, we would not know. We would continue to gaze at its 1,200-year-old light, analyzing its habitable conditions, dreaming of colonization, unaware that we are studying a graveyard. But the delay of light is merely the first layer of the deception. The true horror lies in the violence of the cosmos itself. The universe is not a static, peaceful garden. It is a chaotic, evolving engine of destruction. And the primary executioner of planets is often the very thing that gives them life, their host star. When we hunt for exoplanets, we use indirect methods. We watch for the tiny, rhythmic dimming of a star's light as a planet passes in front of it, a technique known as the transit method. It is like spotting a moth flying in front of a distant lighthouse. This tells us the planet's size and how long it takes to orbit. From this, we calculate if it sits in the Goldilocks zone, the region where temperatures are just right for liquid water. However, habitable describes a location, not a condition. It is a geometry, not a guarantee. And this geometry is treacherous. Most of the habitable planets we have discovered do not orbit calm, yellow suns like ours. They orbit red dwarf stars that are smaller, cooler, and dimmer than the Sun. These stars are the most common in the galaxy, and they are excellent targets for planet hunters. Because they are dim, the habitable zone must be extremely close to the star. To be warm enough to have water, a planet must huddle next to a red dwarf, like a camper shivering next to a dying fire. And this proximity is a death sentence. A planet orbiting this close to a star falls victim to tidal locking, Shutterstock. Just as our moon always shows the same face to Earth, these planets are locked in a gravitational embrace with their sun. One side of the planet is baked in eternal scorching daylight, while the other is frozen in perpetual icy night. The habitable band is merely a thin twilight strip between fire and ice. But even this precarious existence assumes the star is kind. Red dwarfs are not kind. They are temperamental, violent beasts. They are prone to stellar flares, eruptions of radiation and plasma that dwarf anything our Sun produces. Proxima Centauri, our nearest stellar neighbor, is one such red dwarf. Its planet, Proxima b, lies in the habitable zone, but Proxima Centauri frequently unleashes flares that are hundreds of times more powerful than solar flares. Imagine a world constantly bombarded by X-rays and ultraviolet radiation so intense that it sterilizes the surface in seconds. This is not a rare event. It is a daily reality for these worlds. When we detect an Earth-sized planet in the habitable zone of a red dwarf, our data tells us it has the right mass and the right orbit. We assume it is a rocky world. We hope it has an atmosphere. But the physics of the universe suggests a darker outcome. Over millions of years, these violent flares act like a cosmic sandblaster. They strip away the planet's atmosphere, layer by layer. They tear apart the ozone layer, boil off the oceans, and scour the surface until nothing remains but irradiated rock. So when we look at Proxima b, or the 7 worlds of the TRAPPIST-1 system, Shutterstock, and we see potentially habitable worlds, we are likely looking at the cosmic equivalent of bleached bones in a desert. We calculate their surface temperatures based on the assumption that they have atmospheres like Earth's. But if the atmosphere was stripped away a billion years ago, the planet is not a cradle of life. It is a vacuum-sealed tomb, colder than Mars or hotter than Mercury, bathed in lethal radiation. Yet, we cannot see this destruction directly, but our current technology is barely scratching the surface. We see the shadow of the planet, but we cannot yet taste its air. We infer the presence of water, but we cannot see the oceans. We are like a doctor, trying to diagnose a patient by looking at their shadow from a kilometer away. We can see the shape, but we cannot see if the heart is beating. There is another, more insidious way a planet dies before we ever find it. Cool. It is not murdered by its star. It commits suicide. To sustain life as we know it, a planet needs more than just the right temperature. It needs a heartbeat. It needs a molten, churning core of iron that generates a magnetic field. This magnetic field is the invisible shield that deflects the solar wind and cosmic radiation. Without it, the atmosphere is slowly eroded into space. Mars is the perfect example of this tragic fate. Mars lies on the outer edge of our Sun's habitable zone. Once, billions of years ago, it had thick atmospheres, rivers, and perhaps even vast oceans. But Mars is smaller than Earth. It lost its internal heat faster. Its core cooled and solidified. When the core stopped churning, the magnetic heartbeat stopped. The shield fell. And then, the Sun slowly stripped Mars of its air and water, turning a wet, living world into the frozen, rusty desert we see today. Now, apply this logic to the billions of exoplanets out there. We find a planet that is the same size as Mars, in the habitable zone of a distant star. We celebrate. We write papers about its potential, but we have no way of knowing if its core is still alive. The light we receive tells us nothing of its internal geology. We could be staring at a planet that died geologically 2 billion years ago. It occupies the right space. It reflects the right amount of light, but it is a hollow shell. This leads us to a disturbing realization about the nature of our search. We are biased by our own existence. We look at Earth, a planet that has remained habitable for roughly 4 billion years, and we assume this stability is the norm. But Earth is an anomaly. We have danced on a knife edge for eons. We have a large moon that stabilizes our tilt. We have a magnetic field that refuses to die. We have plate tectonics that recycle carbon. Most planets are not so lucky. The universe favors entropy. It favors dead rocks. The window of habitability for a planet might not be billions of years. It might be short, a fleeting breath of a few million years before a runaway greenhouse effect turns it into Venus, or a cooling event turns it into Mars. When we gaze across the galaxy, searching for Earth 2.0, we are playing a game of probability, where the odds are stacked heavily against us. We are scanning a galaxy that is 13 billion years old. The brief flicker of time that a planet is alive with liquid water and a stable atmosphere is a microscopic fraction of that timeline. What is the likelihood that we look at a specific star at this specific moment and catch a planet in that brief, fragile window of life? It is far more likely that we are catching it before it is ready, or long after it has failed. And this is just the destruction caused by the planet's immediate environment. We haven't even touched upon the external threats, the cosmic assassins that roam the spaces between stars. For a planet to survive long enough for us to discover it, It must dodge bullets that are fired from across the galaxy. Consider the immense timescales involved. A light year is a measure of distance, but it is also a measure of isolation. If a planet is 500 light-years away, we are disconnected from its reality by 500 years. But the light carrying the information of its destruction, the wavefront of a cataclysm, travels at the same speed as the image of the planet itself. If a supernova explodes in the vicinity of a habitable world, it drenches that world in high-energy gamma rays. This radiation can destroy the ozone layer of an entire planet instantly, exposing all life to lethal UV radiation. A mass extinction event occurs in a matter of days. The vegetation dies, the food chain collapses, and the planet turns brown and sterile. But here on Earth, gazing through our lenses, we would not know. The light of the star would continue to shine steadily. The dip in brightness as the planet transits would continue like a metronome. For hundreds or thousands of years after the extinction event, human astronomers would look at that data and say, conditions there are suitable for life. We would allocate billions of dollars to build ships or probes to send a message, not realizing we are calling out to a tombstone. This disconnect between the observed image and the physical reality creates a cosmic mirage. We are mapping a galaxy that effectively no longer exists in the state we see it. It is an archaeological dig where the artifacts are made of light, and the civilizations we imagine are merely ghosts haunting the data. The very methods we use to find these planets, the transit method, favor planets that are close to their stars. And as we have established, being close to a star is a dangerous game. The sample of planets we have is heavily skewed towards these perilous worlds. We are like someone walking through a battlefield after the war is over, pointing at the bodies and wondering if they might be sleeping. It is a sobering thought. The silence of the universe might not be because life is rare, it might be because life is fleeting. And by the time the signal of life, the oxygen in the atmosphere, the green of the forests crosses the vast ocean of vacuum to reach us, the source has already been extinguished. We are lonely not because there is no one else, but because our timelines do not overlap. The distances that break our brains also break our connection to the present. We are forever trapped in the past of the cosmos, observing the light of stars that may have burned out and planets that have long since crumbled. As we stare into the eyepiece, searching for a twin of Earth, we must ask ourselves, are we looking for a home, or are we merely cataloguing the ways in which worlds die? The universe is a graveyard of potential, and we are the caretakers, reading the dates on the headstones long after the mourners have left. And the tragedy is, we don't even realize we are standing in a cemetery. But the death of a planet is not always caused by fire or ice. And sometimes, the threat is far more subtle and far more terrifying because it comes from the very thing that makes the universe majestic, its sheer, unfeeling vastness. As we peel back the layers of this cosmic onion, we find that the galaxy has mechanisms of sterilization that we are only just beginning to understand. Mechanisms that ensure that even if a planet survives its star, even if it keeps its atmosphere, it is still doomed before we ever lay eyes on it. The silence of a planet is deceptive. When we observe a world like Kepler 186f, which sits comfortably in the habitable zone of its star, we see a stable orbit. We calculate its mass. We imagine gravity similar to Earth's, but we cannot hear its geology, and it is deep beneath the surface, thousands of kilometers under the crust, where the true life or death struggle of a planet takes place. A planet is not merely a rock in space, it is a machine, and to sustain life, that machine must be running. It requires active plate tectonics to recycle carbon and regulate the temperature. It requires a churning, molten core to generate a magnetic field. This magnetic field is the only thing standing between a fragile atmosphere and the stripping power of stellar winds. However, planetary engines run out of fuel. Over billions of years, a planet's core cools down. As the heat dissipates into space, the churning stops. The magnetic dynamo grinds to a halt. The shield collapses. To our telescopes, the planet looks exactly the same. It is the same size, in the same orbit, reflecting the same amount of starlight, but it is effectively a corpse. This is the internal death. It is a silent killer that leaves no immediate mark on the exterior. That we could be staring at a planet that lost its magnetic field 200 million years ago. Since then, its atmosphere has been slowly bleeding into the vacuum, its water molecules broken apart by radiation, its hydrogen escaping into the void. By the time our instruments are sensitive enough to detect the thinning atmosphere, the process will be irreversible. We are essentially gazing at a patient who has already flatlined, but whose body is still warm. But if the internal death is slow and quiet, the external threats are sudden and violent. We often forget that our solar system is located in a relatively quiet, the suburban neighborhood of the Milky Way. We are lucky. Out there, in the dense, chaotic regions of the galaxy, stars live and die with terrifying ferocity. Consider the supernova. When a massive star ends its life, it explodes with the brightness of 1 billion suns. If such an explosion were to occur within 30 to 50 light-years of a habitable planet, the consequences would be apocalyptic. The intense radiation would strip the planet's ozone layer in an instant, exposing the surface to lethal ultraviolet light from its own star. The food chain would collapse. The surface would be sterilized. Now, recall the tyranny of light speed. Imagine a star 1,000 light-years away from us explodes today. The light of that explosion, the visual evidence of the catastrophe, will not reach Earth for 1,000 years. For the next millennium, astronomers on Earth will continue to look at any planets orbiting nearby stars and classify them as potentially habitable. We will continue to dream of visiting them. In reality, those worlds are already dead, bathed in radiation that we cannot yet see. The news of their destruction is traveling towards us. But until it arrives, we are blissfully ignorant, falling in love with ghosts. When more terrifying, are gamma-ray bursts, focused beams of energy from collapsing stars that are the brightest electromagnetic events in the universe. A gamma-ray burst can travel across thousands of light-years, a cosmic sniper shot that incinerates everything in its path. A planet could be hit by such a beam, sterilized, and left spinning in the dark. But, because the beam is narrow and the event is short, we might never even see the burst itself. We would simply see a planet that should have life, but strangely, does not. We would see the stage, but the actors would have been wiped out long before the curtain rose. This brings us to the most humbling realization of all. We are not doing biology, we are doing archaeology. When we study the universe, we are digging through layers of time. The farther we look, the older the information. We are excavating the history of the galaxy using photons instead of shovels. This fundamental disconnection in time creates what we might call the statistical silence. We often ask, where is everybody? If there are billions of stars and billions of planets, surely the galaxy should be teeming with life. We expect to pick up radio signals, to see megastructures, to find something. But the silence is deafening. That perhaps the answer is not that life is rare, but that life is temporary, and our window of observation is out of sync. Civilizations, ecosystems, and biospheres may rise and fall like waves in the ocean. They might flourish for a few million years, a B of an eye in cosmic time, and then succumb to an asteroid, a nuclear winter, or a stellar flare. But because of the vast distances, we are likely missing the show. That we might be looking at a star system today that hosted a thriving civilization 500 years ago, but by the time their radio signals reach us, they are gone. Or conversely, we might be looking at a planet that will host life in 1 million years, but right now, in the light reaching our telescopes, it is still a toxic volcanic hellscape. We are two ships passing in the night, separated not just by space, but by the impenetrable wall of time. To understand how truly isolated this makes us, we must flip the perspective. Imagine an alien astronomer sitting on a planet in the Andromeda Galaxy, 2.5 million light-years away. They point their super-advanced telescope at the Milky Way. They zoom in on a small yellow star in the Orion Arm. They find Earth. What do they see? They do not see the Great Wall of China. They do not see the city lights of New York or Tokyo. They do not hear our radio broadcasts or our television signals. They see the light that left Earth 2.5 million years ago. They see a planet of wild jungles and savannas, where early hominids are perhaps just beginning to walk upright. They see a world without humans. To them, Earth is a potentially habitable planet. They might mark it on a star map as a candidate for life, and they have no way of knowing that we exist. They have no way of knowing that we have built cities, waged wars, and explored the moon. To them, we are not even a possibility yet. We are the future, and if we were to destroy ourselves tomorrow in a nuclear war, those astronomers in Andromeda wouldn't know about it for another 2.5 million years. They would continue to watch our ancestors, unaware that the lineage had already ended. This is the curse of the light year. It isolates every event in its own bubble of time. It makes a conversation impossible. A simple hello sent to the nearest galaxy would take 2.5 million years to arrive, and the answer would take another 2.5 million years to return. By the time the reply came, the human species might have evolved into something else entirely, or vanished from existence. So, when we read the headlines about Earth 2.0 or new habitable worlds, we must temper our excitement with this sobering context. The universe is not designed for us to find friends. It is designed to keep secrets. The distances act as a natural quarantine, ensuring that no two civilizations can easily touch, or perhaps even know of each other's current existence. Most planets are dead before they are discovered, because discovery is an act of looking into the past. We are viewing the universe through a rear-view mirror. The lush, green worlds we imagine are likely brown, irradiated wastelands in the present. The signals we search for may have ceased broadcasting millennia ago. Does this make the search pointless? Does this render our efforts to map the stars futile? No. In fact, it makes them more profound. If the universe is indeed a graveyard of worlds, a place where life is fragile, fleeting, and constantly under siege from radiation, cold, and time, then our existence here and now becomes infinitely more valuable. We are the lucky ones. We are the winners of a cosmic lottery against odds so staggering they are impossible to calculate. We are on a planet with a magnetic field that has held for billions of years. We orbit a star that has remained relatively calm. We have dodged the gamma-ray bursts and the wandering black holes. We are conscious, we are alive, and we are capable of looking up. The fact that we see so many dead worlds, so many hostile environments, and so much silence should not depress us. It should wake us up. It highlights just how special Earth is. It is a pale blue dot suspended in a sunbeam, surrounded by an ocean of darkness and dead rocks. We are not merely inhabitants of a planet. We are the custodians of a rare and precious flame. The silence of the universe is a reminder that we are, for all intents and purposes, alone. And in that loneliness, there is a responsibility. If we are the only ones who can see the graveyard, then we are the only ones who can mourn the dead, and the only ones who can appreciate the miracle of the living. Our telescopes will continue to hunt. We will continue to find planets. We will continue to analyze their light, searching for the chemical fingerprints of life. But we must do so with the wisdom that what we see is a mirage of the past. The universe is a place of immense beauty, but it is a beauty frozen in time, a gallery of portraits where the subjects have long since moved on. As we look out at the Milky Way, at the billions of stars and the trillions of potential worlds, we are not looking for a new home to escape to. We are looking for a mirror. And in the reflection of those dead worlds, we see the fragility of our own. And we see that survival is the exception, not the rule. So, the next time you see a headline about a new Earth-like planet, do not imagine a paradise waiting for your arrival. Imagine a monument, a testament to what might have been. And then, look down at the ground beneath your feet, breathe the air that fills your lungs, and realize that you are standing on the greatest anomaly in the universe, a world that is not yet dead.